Okay, let's unpack this. Imagine you're this brilliant AI researcher, right? Late nights, loads of coffee, you're pushing the boundaries, trying to make these models do incredible things. So you train your recurrent models, maybe on short sequences, like 2,000 tokens, and they absolutely crush it. Performance is top tier, you're feeling pretty good. But then, okay, you test them on something way longer, like 128,000 tokens, and bam, perplexity spikes, the whole thing just collapses. It's like watching a marathon runner just fall apart right near the end. So you dig in, you check the internal states, and what you see is kind of baffling. The states they saw in training, that's just a tiny, tiny slice, a familiar little valley. But the states, they hit on those long sequences, totally uncharted territory. And then boom, it hits you. They're basically blind. They're blind to like half their own state space, this whole landscape they've never seen. That's it, the unexplored states hypothesis. So, okay, interventions. You try everything. Random noise? You get a little bump for the smaller models, maybe 370 meters, but the 1.3 billion parameter one stalls. Nothing. Fitting noise, okay, that's better. Definitely an improvement, but the really big models, still failing. Still can't handle the long stuff. Then you try state passing. Different idea. Initialize with the final states from other sequences. You give it 500 steps. Tiny fraction, like 0.1% of the pre-training budget, and suddenly, whoa, it works. Your 2K trained model breezes through 128K tokens. Perplexity stays tight, no collapse. It's a breakthrough. You measure this thing, effective remembrance. What you find is nuts. The old models, the failing ones, they were fixated on tokens from way back at the start. Ancient history, ignoring the new stuff. But the intervened models, totally different. They focus on recent context, like they should. Their state distributions stable. No more of those wild, crazy shifts after the training length. You even test TBTT, truncated backpropagation through time, split the long sequences into chunks, pass the state along. Same magic. And it only takes like 100 steps. Done. So you realize it's not really about training on the super long sequences themselves. It's about training on the states that those long sequences produce. That's the key. You try it on Mamba, GLA, RWKV, different architectures, all respond. Same fix works across the board. And you think, wait a minute, length generalization isn't actually that hard. It's just about exposing them to the states they're actually going to meet out there. You don't have to rebuild the model. You need tons more data. You just show them the states they were missing. And now they handle sequences orders of magnitude longer. You didn't just put on a Band-Aid. You built a bridge between training and, well, every long sequence yet to come. Welcome to the deep dive. Today, we're unraveling a really fascinating breakthrough in AI specifically, how we can teach machines to remember, to really remember, over these incredibly long stretches of information. Our mission for you, the listener, is to cut through all the jargon, all the complexity, and get right to the core insights of this research. We want to reveal how a problem that seemed almost insurmountable was cracked with, honestly, surprising simplicity.
It's fascinating, isn't it? Because this isn't just, tweaking an algorithm here or there. It's about fundamentally understanding why these models were hitting a wall with long sequences, and then finding this remarkably elegant solution. We're talking about recurrent models, things like state space models. Mamba is a big one people talk about, or linear attention variants like GLA. These are quite different from standard transformers. They process information step by step sequentially, and they compress all the past context into this single compact state. You can kind of picture it as this constantly updated memory capsule.
Like a running summary of everything it's seen so far.
Exactly. And the beauty, theoretically, is that this design should let them handle arbitrarily long sequences with linear complexity.
Meaning the compute cost grows proportionally with the length, not like exploding quadratically.
Precisely. So on paper, incredibly efficient for long stuff, but the reality, that theoretical benefit often just wasn't there. Performance would tank, sometimes dramatically, as soon as the input kept longer than the training sequences.
Okay, so let's nail this down. Length generalization. What does that actually mean in practice? At its heart, it's just about a model keeping up its performance, its understanding, when it has to process sequences that are way longer than anything it saw during its training phase. Think of it like a student who aces all the short practice quizzes, perfect scores. But then they get the final exam, and it's this massive, long-form paper they've never practiced for. They might just completely bomb it, right? Not because they don't know this stuff, but because the format, the length, just threw them off completely.
That's a great analogy. And in AI, the key metric we use is position-wise perplexity.
Right, perplexity. Lower is better means it's less confused.
Exactly. It measures the model's uncertainty or confusion at each specific point, each token in the sequence. If you plot this perplexity and see a big spikes right after the training length, what we call T-train, that's the sign of failure. It's the model essentially saying, whoa, hang on, I've never been out this far, I'm lost.
So why? Why were they getting lost? That brings us to the core idea, right? The unexplored states hypothesis.
Yes, and it's actually quite intuitive when you break it down. Imagine the model is learning to navigate this huge landscape of possible internal states, representing the context. But during training, it only ever sees this small, familiar valley. It gets really good at navigating that valley, every path, every landmark.
Okay.
Then you test it on a much longer sequence. Suddenly, it's dropped onto a new path, maybe high up in the mountains, encountering unexplored state distributions. Parts of the landscape it's literally never seen. It effectively overfits to that initial training valley. It develops this tunnel vision for the states it saw early on, and it's just not prepared for the full range of states it could encounter the attainable states from processing really long inputs.
And they came up with a clever way to diagnose this, didn't they? This effective remembrance thing.
They did, yes. It's a really neat diagnostic. It essentially measures how much influence tokens from the distant past have on the model's prediction right now. Is it paying attention to the right history?
And for the failing models, what did it show?
It showed something quite stark. For those models that failed at length generalization, the effective remembrance was really high for the very first few tokens in the sequence.
So they were stuck at the beginning?
Pretty much. They were disproportionately impacted by the initial context, like they couldn't let go of the starting line. Imagine trying to follow a complex recipe, but you keep obsessing over the first ingredient, 2 cups of flour, 2 cups of flour, even when you're supposed to be adding the final touches. That early information just swamps everything else.
Okay, that makes sense. So the short training context was a big part of it. Not enough variety.
Definitely. Short contexts inherently limit exposure. And crucially, the bigger the model, the more complex its state, the longer the context it actually needs during training to learn to generalize well. It's not one size fits all.
And training longer didn't always help? That seems weird.
It is counterintuitive, but yes,
Yeah.
extended training beyond a certain point could actually make things worse. Models could start to overfit even more intensely to those limited states they saw during training.
Huh. More than you'd expect just from normal scaling laws.
Exactly. More than something like chinchilla scaling would predict. It pointed to a specific kind of failure mode, not just needing more general training.
Mm-hmm.
And another piece was the zero initialized state, starting every single sequence fresh from absolute zero.
Like hitting the reset button every time.
Precisely. It constantly reinforces the model's focus on those early sequence states it always sees when starting from zero. It never gets a chance to learn how to handle states that only emerge much deeper into a sequence.
Okay, and the last bit was the state distribution itself kind of going haywire?
Right. For these struggling models, their internal representation of context, that state or memory capsule would actually shift significantly and unpredictably once they went past their training length, T-train. It was like the internal compass just started spinning wildly. Uncharted territory indeed.
All right, so problem identified. Unexplored states. Tunnel vision. The solution then seems almost obvious in hindsight, right? Just show them more states.
Essentially, yes. That was the core idea behind the interventions. Not necessarily more data in the traditional sense, but exposure to a wider variety of initial states.
And they did this with these quick post-training tune-ups, the interventions.
Exactly. Surprisingly simple modifications to how the model started processing each sequence, and incredibly efficient.
Yeah, you mentioned like 500 steps. 0.1% of the pre-training budget. That's tiny.
It's remarkably small. It suggests the core capability was already there, just locked behind this initialization problem.
So the first try was random noise. Just start with random numbers instead of zeros.
That was the first attempt, yes. Initialize the state by sampling values independently from a standard Gaussian distribution. Simple idea.
How'd that go?
It gave a slight improvement for smaller models, but it pretty much failed for larger ones. The big 1.3 billion parameter models barely budged.
Why not?
Yeah.
Too simple.
It seems so. It highlighted that just throwing any kind of noise at the problem wasn't enough. The actual distribution of those attainable states in long sequences is much more structured, more complex, especially for bigger models. Simple independent noise didn't capture that structure.
Okay, so then they got smarter with fitted noise. What was different there?
With fitted noise, they still used a Gaussian distribution, but critically, the mean and standard deviation of that Gaussian were dynamically fitted. They were matched to the statistics of the final states the model actually reached during its normal training phase.
Ah, so noise, but noise that kind of looks like where the model should end up.
Exactly. Noise tailored to the model's own learned state distribution. And this worked significantly better. It boosted generalization for the smaller and medium models, like the 370-meter and 780-meter Mamba 2s. They could handle longer sequences.
Still not the biggest ones.
Still not the 1.3 billion parameter model.
Hmm.
It improved, but didn't fully solve it. It suggested that even fitted independent sampling couldn't quite capture the complex dependencies between different elements within the state of these very large models. The state isn't just a collection of independent numbers, they're related.
Which brings us to the star player, state passing. This sounds really different.
It was a conceptual leap, and it turned out to be the game changer. Instead of zeros or any kind of engineered noise, they did something really clever. They initialized the state for the current sequence using the final state from a different sequence processed in the previous training batch.
Wait, so you finish processing one chunk of text, grab its final memory, and use that to start the next chunk.
Precisely. You're essentially jump-starting the model with a state that it would naturally arrive at after already having processed a decent amount of information. The paper describes it as being equivalent to sampling an initial state directly from the distribution of attainable states.
You're basically giving it a warm start using a realistic, long sequence state.
Exactly. And the results were dramatic. State passing was highly effective. It enabled robust length generalization across the board, even for the largest models. We're talking models trained on 2K tokens suddenly handling 128K tokens without breaking a sweat.
Wow. And that fixed the effective remembrance issue, too?
It did. It significantly reduced the influence of those very early tokens. The model started focusing correctly on the more recent, relevant context. And crucially, it stabilized that internal state distribution. No more wild shifts past tier train. It kept the model operating within a familiar, predictable state space.
Okay, and then there was TBTT, truncated backpropagation through time. How did that fit in?
TBTT is a standard technique for training recurrent models on long sequences by breaking them into chunks. What they did here was pass the final state of one chunk as the initial state for the next chunk within the same sequence.
Kind of like state passing, but within one continuous stream.
Exactly. And the magic, as the paper calls it, was that this achieved very similar performance to state passing, almost identical results.
Which really proves the point, right? It's not about seeing one single massive sequence during training.
Exactly. It drove home the point. It's about training on the states that long sequences produce. You don't necessarily need to feed it a 128K token sequence in one go during training. You just need to expose it efficiently to the kind of internal states it will encounter when it does see such a sequence in the real world. State exposure is key, not just raw sequence length during training.
So this wasn't just about making perplexity graphs look prettier. These fixes actually made the models better at real tasks.
Oh, absolutely. That's the crucial connection. These weren't just theoretical tweaks. They genuinely enabled the models to leverage dependencies across much longer distances and perform well on actual reasoning tasks that require understanding long contexts.
Like that Babylon benchmark you mentioned.
Right. Babylon tests common sense and tracking information over long narratives. State passing and TBTT showed significant improvements over the baseline models there, even pushing performance on sequences up to 256,000 tokens long, remember, from models trained only on 2K. That's a massive practical jump.
That is staggering. And the passkey thing, finding a needle in a haystack.
The passkey retrieval task, yeah. Tough
No.
challenge. Here they used fitted noise for fine-tuning a specific choice because the data changes character right near the passkey.
Non-stationary. Got it.
And this allowed models to find that passkey in sequences at least twice as long as their training context. The 780-meter model even got perfect accuracy on 256K sequences. Finding a specific 5-digit number buried that deep is really impressive.
No kidding. And even simple copying improved.
Yes, on a synthetic copying cast, state passing significantly improved the accuracy for copying sequences more than 3 times longer than the training length. It shows the benefit applies to fundamental sequence processing too. These are real capability unlocks.
So stepping back, what's the big picture implication here for AI development? This feels pretty significant.
It really is. The research strongly suggests that length generalization in recurrent models is expected to be readily achievable through simple training interventions. That's a powerful statement.
It means researchers don't have to obsess quite so much about training on massively long sequences from the start.
Exactly. They can focus more on optimizing the model's core performance, its in-length performance, within a manageable training context length. knowing that they can likely add robust length generalization later with an efficient tune-up like state passing or TBTT.
That must free up a lot of resources and potentially speed up innovation in new architectures.
It should. And importantly, unlike some previous attempts that involved complex architectural changes, these interventions do not change the implementation of the architecture itself. They're simple add-ons applicable to various models, Mamba, GLA, RWKV, potentially others. It simplifies the whole process.
It's like adding a turbocharger later instead of redesigning the whole engine from scratch.
That's a good way to put it. It makes development more modular.
So where does this point research next? What are the open questions?
Well, the paper itself lays out some clear paths. One obvious direction is exploring if this holds true for other types of data beyond text, like long audio streams, financial time series, or even genomic data. Do the same principles apply?
Makes sense. What else?
Testing a wider variety of recurrent architectures is another key area. Does this unexplored states hypothesis apply universally to different recurrent designs, maybe even hybrid models that combine recurrence with attention?
And pushing beyond just recall.
Yes, further connecting this hypothesis to more complex algorithmic extrapolation tasks. Can these interventions help models not just remember long sequences, but actually reason and perform complex algorithms over them? There's a lot of exciting work still to be done building on this foundation. It feels like we've just scratched the surface of what these models can do once we address these state limitations.
So, wrapping up today's deep dive, we've seen how this really clever idea, the unexplored states hypothesis, combined with surprisingly simple, super efficient interventions like state passing, has effectively built a bridge for these recurrent models, letting them finally grasp information over these vast distances they struggled with before. It's just a fantastic example of how deeply understanding why something is failing can lead to elegant, powerful solutions.
It really is. Sometimes the simplest ideas, born from clear insight, have the biggest impact.
And think about this. Just by showing a model the states it was missing, just by letting it see the full landscape of its own potential memory, we unlocked entirely new capabilities. It really makes you wonder, doesn't it? What other blind spots might our current AI models have? What other hidden limitations, if we could just find them and illuminate them, could lead to the next big leap in intelligence?
That's the million-dollar question, isn't it?
Something to ponder. Keep exploring, keep asking questions, and keep digging deeper. Until next time, this has been The Deep Dive.